Let's pretend you are a 6-year-old. At the playground today, you're having a competition with one of your friends. Your friend, who also happens to be 6 years old, challenges you to a number battle. What is a number battle, you might ask? It's simple. You both take turns saying numbers until one person can't name a number that's higher than the previous number. How long would this game last? You might argue that this game would last forever, because you could always say a number that's one higher than the previous number. And you would be in good company. Many mathematicians would agree that this is a good way to model how we think about numbers and counting. They've even created an entire set of rules for numbers, called the Peano axioms, that take a lot of inspiration from this idea. A central focus in these rules is a thing called the successor operator, which we can think of as a function telling us which number comes next after the previous number. Let me give you a quick overview of what these axioms are. The first axiom states that 0 is a number. The second axiom states that for each number, the successor of that number is also a number. You can think of this as meaning that for each number, the number plus 1 is also a number. The third axiom states that 0 is not the successor of any number. We are not considering negative numbers here. These axioms are meant to represent only the positive integers, which is why we have this rule. Finally, there's two other axioms about equality and induction, but they are not relevant for the point I want to make. It's very important to emphasize that the Peano axioms are simply a set of rules we came up with that model the concept of numbers that we experience. We can think of having no apples or having one apple, and if you can imagine that we have n apples, we should also be able to imagine having n plus 1 apples, right? But we could also choose a different set of rules to model numbers. I'd like to argue that there exists a mathematical model that more accurately describes how we actually think of numbers. I believe that we should impose a limit on how far we can count. This means that in this model that I propose, instead of stating that for each number we have a successor, we would state that the numbers have a successor up to some specific maximum number. This maximum number has no successor and is the biggest that we can get. So instead of having infinitely many numbers, we are only working with a finite amount of them. Introducing this finiteness of counting might sound very strange at first, but let's remember that us humans are very finite creatures as well. We live a finite number of years, with each year consisting of a finite number of days and each day consisting of a finite number of seconds. And if you're lucky, your brain, made of finitely many neurons, might have a few thoughts each second. Just like a computer only has a finite amount of storage in their silicon brains, so do we only have a finite amount of storage and only a finite amount of time to have finite experiences. A logical consequence of this is that there is some largest possible number that you, as a person, are able to experience. Even if you would spend your entire life only focused on conceptualizing the largest number possible, it would always be finite. Therefore, I argue that a mathematical model that is supposed to represent how we think about numbers should also contain this idea. I assume that you're probably not convinced yet that limiting ourselves in this way is beneficial. After all, so many nice theorems that we have constructed disappear in this finite universe. Take Euclid's theorem, for example, which states that there are infinitely many primes. This theorem would no longer be true because a finite amount of numbers implies a finite amount of primes. But hold on, let's take a step back here. Is having infinity here actually helpful? Do we really need infinity to state the information that we want to state? Let's imagine that we have another type of number with some property that makes them unique. Let's call them line numbers. Imagine that there exists a theorem stating that there are infinitely many line numbers. But let's also imagine that it turns out that the smallest line number is already so big that the size would be incomprehensible to humans. We would never be able to write down or use these numbers in any context. I don't think these line numbers nor this theorem would be very useful to us humans. So why is Euclid's theorem actually useful? The usefulness of the theorem is that it tells us that we can expect to find primes of reasonable size, but that only becomes obvious when we word it in a different way. If you look at the proof of the theorem, we can see that the actual statement that contains the information we want is, if we have a set of prime numbers p1, p2 up to pn, then there exists another prime number less than or equal to the product of those prime numbers plus 1. This is what Euclid's theorem actually tells us. It's about the density of primes, when we can expect primes. And there's a nice bonus. This version of the theorem is still true in the model I propose, where we have a largest number. Well, there's still one thing that I need to clarify. In our finite model, addition and multiplication are not properly defined yet. As mentioned earlier, in our finite model we have some largest number, let's call this n. Now it could happen that we have some numbers a and b that are defined, but a plus b or a times b might not be, if they are bigger than n. To solve this problem, let's think about how to rigorously set up the rules for addition and multiplication by going back to the successor operator. The successor operator still works the same as in the Peano axioms for numbers up to n-1, but the successor for n is undefined. This means that the successor is no longer defined for all numbers, which is what you would call a partial function. These are not unusual in mathematics. For example, in calculus, the function 1 over x is not defined for x equal to 0, or even more extreme, the function log of x is not defined for x less than or equal to 0. By writing multiplication as repeated addition and addition as repeatedly adding 1, we can see that we can always express any combination of these operations as repeatedly applying the successor operator. Because we know that the successor of n is undefined, this implies that as soon as we need to calculate the successor of n anywhere in our computation, the answer becomes undefined. This might seem like a very big restriction on addition and multiplication, but I argue that it's not, as long as we choose n to be large enough. I mentioned previously that as a consequence of our finite nature, there is some largest number that a human is able to experience. Let's choose n to be this number. This implies that if we have two numbers a and b such that the sum a plus b is greater than n, we would not be able to comprehend the number a plus b by the definition of n. Therefore, the restriction I put on addition is actually not a restriction at all, just a natural consequence of the ideal we started with. Any actual addition we want to do will always be with numbers that are comprehensible with a sum that is also a number that we can comprehend. And the same argument holds for multiplication too, of course. So far, I've only talked about the restrictions of this finite model, but let me also talk about the thing we gain, which in my opinion far outweighs the negatives. If we use the Peano axioms in combination with addition and multiplication, or any other set of axioms capable of doing basic arithmetic on the natural numbers, then we have to deal with Gödel's incompleteness theorems. In simple terms, the first theorem states that within this system of rules there are statements that are true but we cannot prove to be true using the logic of the system itself. The second theorem states that using the logic of the system we also cannot prove that the system doesn't have any contradicting statements, which is what we would call a consistent system. But notice that for our finite system we cannot do basic arithmetic on the natural numbers, so Gödel's incompleteness theorems do not necessarily have to be true. And in fact, I do believe that the first theorem does not apply here. If we have any statement about this finite set of numbers, we can verify it by simply checking all the numbers. Let me illustrate this by going back to Euclid's theorem, stated in the finite compatible way that we talked about before. We can prove that for each set of prime numbers p1, p2 up to pn, such that the product p1 times p2 times pn exists, there exists another prime number less than this product by simply verifying that it is true for each set. This would be one way to prove Euclid's theorem. It would take an extremely long time and is very inefficient, but it still counts as a proof. Now this does not mean that under these rules creating proofs is dead. It just requires an adjustment of our way of thinking about proofs. The only thing that actually changes is that we know that for any statement about this finite collection of numbers, there exists a way to show that the statement is true or false. So instead of asking the question, can we prove this? The job of mathematicians becomes thinking about the question, does a simpler proof exist? We still have to put in the usual effort to prove statements this way. This is just my personal opinion, but I think that Gödel's incompleteness theorems do not teach us that all mathematical systems have some kind of fundamental shortcoming, but that our mathematical systems are not the ones we should be using. The way I see it, we modeled math after an idealized picture we had of how we do math, but by idealizing our human brains we oversimplified the practical reality of what doing mathematics actually is like. Infinity is simply too big for our human logic to handle in any kind of meaningful way. There's just too much stuff, too many numbers, too many statements that it becomes inevitable that there will be holes that we cannot plug up. This is not the final video I want to make on this topic. I believe there are even more sophisticated ways to have finite systems that extend to other areas of mathematics, such as calculus. I also plan on making videos on other philosophical topics that are not related to mathematics. If you're interested in these kind of things, then feel free to subscribe. See you next time.